2.9 is a one-day lesson. Then we go on to 2.10 tomorrow. There is a quiz I opened today on College Board. It's on 2.8, which we learned before the break, so you might need to go back and look at that. And then this one-day lesson, it's open through Friday. 10 questions, multiple choice, same old deal. Then we are going to finish 210, 211, and 212. And that will be the end of our semester. And we'll have a test the end of next week, Friday, and then the Monday. So we really have only new stuff this week and next week. And one of those days is a work day. One of those days is the FAST testing. So I think after today, there's only 4 or 5 new lessons left. Then we'll work on exam review and all that stuff. Also, oh, if your other teachers didn't tell you, they want you to bring your laptops tomorrow for like setting up stuff for FAST testing. 9th and 10th graders and 11th and 12th graders, they said you guys are going to do something. I don't know what it was, but so just try to bring your laptop tomorrow, especially 10th grade, but they said everybody. Okay. This is not going to be too hard today. You should have no problem finishing homework in class. Yay. And then, and I also want to say that we're doing logarithmic expressions. We're working on kind of learning about logs. I'm going to take it further over the next couple of days. And everything I'm covering today was probably covered in your Algebra 2 class. But, you know, when I say that, I don't mean like you should remember it. It's just, you might be like, I remember doing this. It's nothing new from past. Okay, so logarithms are inverses of exponential functions. And you're going to see that in a second. It's just another way of writing some mathematical information. And it's really sciencey based. There's lots and lots of logs in science, and you'll see that in our word problems, right? And logs are really beneficial in solving for variables that are in the exponent, and we'll see that too. Okay, so just understand we're just learning about logs. They've got some special properties about them and ways of writing them. And here's some of the basic properties of logs that I'm not going to go through them all, but I will say that these two right here are like the hardest for me to explain, and they're going to pop up a few times throughout the lesson, and I'll say these are those two weird ones that I was talking about, and I'll talk about them more in a second. But like I said, logs can be rewritten as exponential functions, and exponential functions can be written as logs. So that's the first thing we're going to do. It's the most of what we're doing today. It's just learning how to rewrite them. There's no calculator involved. It's just knowing where every number or letter stands, okay? So let me read a log to you first. The way you would say this out loud would be log base 2. So that little subscript number is your base. Log base 2, then you would say of 8 equals 3. So log base 2 of 8 equals 3. And this is a true statement because, and I'm going to write it in its exponential form, we start with the base, so log base 2, okay? And you'll see in the beginning, like it's helpful to draw these like arrows. 2 to the power of 3 equals, and then there's just one number left, 8. And that's a true statement. 2 to the third power does equal 8. Okay? Same thing here. Log base 3, so base is 3 of square root of 3, equals 1/2. So 1/2 is my power, and then equals the square root of 3, which is true. The square root of 3 we can rewrite with a fraction exponent. Remember, it's 1/2. Okay. Base 5, power would be -2, equals the only number left. Another true statement, remember, if you have a negative exponent and you want to make it positive, you just cross the fraction bar. So if this is like 5/1, right? So if I bring 5 to the denominator, it makes it a positive 2, which is 1/25. And we're going to really have to know how to work with the negative exponents. Okay? It's really important that you know. We'll review it again in a second. This one is called a common log. It says it up here, we talk about it more on the next page, but common logs are a base of 10. So when you don't see a subscript, you know it's a base 10. So it's the same as saying this. Okay, that means this. It's kind of like if I asked you what number's in front of this x, you all know that it's a 1, but we don't write it, right? If you just see an x by itself, you know it's 1x. If you see an x with no power and I asked you what the power was, you would all know that it's a power of 1. We just don't write it, right? It's just known. Same thing here. If you don't see a subscript number, it's 10. Okay, so base 10 to the power of 1 equals 10, which of course is a true statement. This is one of those weird ones I just mentioned. Really intelligent math word there, weird, one of those weird ones. What I want you guys to notice is 6 log base 6. We don't really rewrite this another way. I just want you guys to see, whenever you see that, it just cancels out, okay? 6 to the log, it's always going to be the same numbers there, and then 11 equals 11, okay? And we're going to keep seeing that over and over again. This is the same as what you see here, where the b's are the same. This base is the same as this number. It's just x equals x. Whatever's there equals that. So you're going to see that again and again. And it starts just to become like easy to recognize because they're the same number. It's never going to be like 6 to the power of log base 4. They're always going to be the same number, and you're going to be like, oh yeah, it's that weird one. We cancel it out. Whatever's left is left. Okay, we'll see it again in a minute. Right? So what we're going to do now is write exponential functions, right? 4 to the power, exponent 3 equals 64. Write it in log form. So if you're going to write something in log form, it has to have the word log in it. Okay? So that's what we start with. We start by writing the word log. Okay? And the base comes next. Log base what? Well, in an exponential equation like this number is called the base as well. It's a base of 4 to a power of 3. So the base of an exponential is the base of a log. Okay? Now this is how I teach it in the beginning, just so you can remember where everything goes. I say leave a good space there and put an equal sign. Leave a space. So it's log base 4 of something equals something. Okay? And there's 2 numbers left. There's a 3 and a 64. We're going to put them somewhere. So this is how I describe it. This 3, he's up in the air, right? He's a power up in the air by himself. He likes to be by himself. He's the only number in the exponent. Well, he's a loner. He wants to be by himself in the equation too. He goes on the other side of the equal sign. And then that leaves our last number to go right here. These are the ones people make mistakes on the most. So I will remind you that if you know how to go the other direction, which I just taught you, you could easily check this. Now this is not required. I'm just showing you. I could rewrite this as 4 to the third equals 64. Did I get it right? Yeah, they are the same. Okay, so they're easy to check if you're worried that you put something in the wrong place. Because most people don't make mistakes going from logs to exponentials. And we're going to practice those again on the next page too. But it's this direction that people make mistakes on. Okay, let's try another one. Start with the word log. What would the base of our log be? 9. Leave a space, or if you've already figured out the pattern, go ahead and put your number in. Exponent is 3. He's a loner up in the sky. He wants to be a loner when he's back down on the ground. And then that leaves that 1 space for our last number. 9 to the third equals 729. 9 to the third. So log base 2, loner, and we should put this in parentheses. If it's anything other than just a number, put the whole thing, the fraction in parentheses. And one more. Log base 64, loner. Okay, so being able to go from exponential to log form, no math involved, just knowing where everything goes. Good on those? Let's practice going the other direction. We kind of did it in example 1, but there's like the official, just rewriting these in their other form. So we start with the base. Dylan, you should be writing these notes. Start with our base, right? 5 to the third. These are our arrow problems. And your answer should make sense, too. It should be true. 5 times 5 times 5 is 125. 625 to the 1/4 power equals 5. Guys, remember, 625 to the 1/4 is the same as saying this. So 5 times 5 times 5 times 5 is 625. Okay. 1/2 in parentheses to the power of -6 equals 64. So here's the thing. When in doubt about parentheses, I can't think of an occasion where parentheses would be bad. You know what I mean? Like, when in doubt, probably fine to put something in parentheses. Like, here's another example. 2 to the -5 equals 1/32. You don't need parentheses here, but if you were like, oh my gosh, I'm not sure if I should or I shouldn't, it wouldn't hurt to put 1/32 in parentheses, right? It's kind of unnecessary, but it's not, like, wrong, right? But remember, if we want to do something to a power, we're saying to the whole thing. All right? So we have to put that. Right? So being able to toggle between the two forms, right? In this next two examples, I'm going to show you how to do them right in your calculator. Okay? And then we're going to do some that you can't do in your calculator on the next page. So on your calculator, you have a log button right here. That is a common log button. That means if it's a base 10, you can just use that button a lot later. Okay? And if you look, all of these examples here are base 10s. All of them are common logs. So you can just literally type in log 100 and get your answer. Log of 1/1000 and get your answer. Okay? So take a second and try to get these answers. You should get 2 here. Here's another one of those weird ones. I'll go over D in a second. Now listen, there's one of those properties I didn't talk about until now that tells us that anytime the base and the number are the same, the answer is always going to be 1, no matter what. So log base 100 of 100 equals 1. So anytime those are the same equals 1. Here's another one. Why does that equal 1? Because it's a common log. If you don't see a number here, you know it's a 10. Okay? And that's what we have here. Log base 6 of 6 equals 1, and 10 to the first power is 10. Okay? Same with these three. These go right in your calculator, and then you'll round to 3 decimal places. So these are really just rounding exercises. We have to be good at rounding. You do not want to lose points on a test or on the exam because you don't know how to round. When you put C in, it's going to give you error. That number can never be negative. And I'll prove to you on our next page why not. So do we get the calculator, right? You'll have a chance to practice these in your homework too. So if you didn't finish them, it's no big deal. Okay? All right. Now we have these two sections, 6 and 7, where we have not common logs. These all have bases other than 10. We're going to do example 6 without using a calculator, and then I will show you how to use your calculator with bases that are not 10. Those away. Okay? But as you know, we are constantly having tests, and we know at the end, the big test is going to be calculator portion and non-calculator portion. So for me to just show you how to do this with a calculator would not be right. You have to know both ways, okay? So what they want to do is, what is the answer to this? What is log base 2 of 32? So when it's asking me that, I make it into an equation, equals x. That's what I'm going to solve for, right? What does this equal? Equals x. So once I make it an equation, I can rewrite it in exponential form. So 2 to the power of x equals 32. And when it's asking you to do it by hand, in other words, without a calculator, the two numbers you get should be able to be changed into the same base. In other words, we should be able to change 2 into a base 32 or 32 into a base 2. Okay, so you may not know that 32 can be changed to a base 2, but it can if you're being asked to do this without a calculator. So, 2 to the first power, 2 to the second power, 2 to the third power is 8, 2 to the fourth power is 16. Remember, you don't have a calculator, so, you needed to test it if you didn't know. There it is. 2 to the fifth power is 32. Okay, so I'm just going to rewrite 32 like that. Right? 32 is 2 to the fifth. And since the bases equal each other, you can then set the exponents equal to each other. And the answer is 5. So log base 2 of 32 equals 5. Try another one. Equals x, or any letter. I just put x. You can put whatever letter you want. Rewrite it in its other form. 49 to the power of x equals 7. Remember, if you're being asked to do this by hand, you should be able to get them to have the same base. And I think we all know 49 can be base 7, right? So 49 is 7 squared. All I did was change 49 to 7 squared. And there's already a power up there. Hey, how you doing? I'm coming up here to hang out with you. So it's just power to a power we multiply. So 7 squared, there's an x there, equals 7 to the first, right? That's what that means. So since the bases equal each other, we can set the exponents to each other. 1/2, 4.5. Okay, most questions I get on these problems, so watch. 1 over 64 to the power of x equals 4, right? Rewrote it in its other form. And remember, I should be able to make a 64 into a base 4. So 4 to the first is 4, to the second is 16. What about one more? 4. Yep, okay. So 64 is the same as 4 to the third power, okay? So I have 1 to the x still on top, and I'm just going to change 64 to 4 to the third. That's a 3 there. Now remember, we want like bases. They're close, but this is 1/4 and this is 4. We want to bring the 4 up, so it's the same as the right-hand side. So we're allowed to cross the fraction bar if we want to. What happens when we cross the fraction bar? What, Danielle? The 4 and the 1, yes, but of what? Of the 3. So the mistake people make is they change the sign of the base. Okay? When I have, if I have this on the bottom, if I want to move it to the top, I'm allowed to, as long as I change the sign of the exponent. Okay? 1/4 to the positive 3 is the same as 4 to the negative 3. So I'm going to bring the 4 to the third up. The 1 and the 4 multiply, so we just have 4 to the negative 3, and there's already an x there, just like on that last problem, they hang out, equals 4 to the 1. So that was a way of getting them to have the same base. Remember, you're allowed to cross the fraction bar. It just changes the sign of the exponent, not the base. So now I have negative 3x equals 1. Divide by negative 3, and I get negative 1/3. Okay? Here's why this, remember I said this number can never be negative. Here's why. 5 to the power of x equals negative 25. There's nothing I can make this x to get a negative number. Think about it. We know 5 squared is 25. But 5 to the negative 2 doesn't make negative 1.5, or negative 25, it makes 1/25. So there is no number that I can make a negative answer over here. There's no power to make that happen. So that does not exist, no solution, whatever you want to write. But that's always going to happen when we have a negative here. And you saw it on the page before. Okay. Now I'll show you how to do them with the calculator. So before that we just did could have been done this way as well, but remember there's going to be times you have to do it by hand, so please know both ways. Right? So pick up your calculators. You guys know the log button I just showed you is base 10 for common log. So these are all 4 different bases. Really, really easy way of doing it. Find your math button, we've used a lot, and then the button above it is called alpha. You just do math, alpha, math. Just right in a row. Math, alpha, math. And then you should see that on your screen. And then you could just fill in. See, it's already got the cursor where your base is, so I'll put a 3, and then I'll put the 15, and then you just hit enter. And these you're going to get decimals. Okay? And you should be doing this on your calculator so you know how to do this when I'm not around. So, math, alpha, math. I'm just doing this one right now. 0.35, 8.4. So, if you want to finish these, fine. But, again, it's just a rounding stitch. You'll do it in your homework. Okay? Math, alpha, math. Math, alpha, math. So if any of you missed that wasn't sleeping, let me know when we get to the homework. We're almost there. There's one more problem to do. But any question on this page before we go to our last problem? Good. All right, last problem is a Richter scale problem. I kind of geek out on this problem because I just think it's really interesting. Remember I told you, we are really closely related to our science friends. We do a lot of their math for them. They come up with these kind of crazy formulas and we say, okay, we can solve it. But like I said before, there's a lot of logs in sciencey questions. And here's a really, really common one. The intensity level I of 2 earthquakes measured on a seismograph can be compared by this formula. So here is a formula that you don't have to memorize. It would be given to you, where M is the magnitude given by the Richter scale. So you might have heard on the news, like there was this earthquake with a magnitude blah, blah, blah. Okay? This is really a cool formula to compare the difference in intensity. What does a magnitude give us? Not a lot of information. So look, how many times more severe or intense was this earthquake in India that was measured as a 7.9 than the earthquake in Greece that was measured at a 5.9, okay? So we're going to use that formula, and what we're doing is plugging in M1 and M2. And you really always do the bigger number minus the smaller number. So we should get a positive answer on that side. So it might not say M sub 1 and M sub 2. We just want a positive number. Difference in the intensity should be a positive number. Okay, now our little science people, they set this up with the log of the difference in intensity. That's what we're trying to find. What is the difference in the intensity? Okay? They called it I sub 1 over I sub 2. And I remember, honestly, being a youngster like you and being confused by that. Because what's going to happen is your answers, well, I'll get to it in a second. I'll come back to that idea. So what I see here is a log equation, and I know I can write this another way. There's no way to put this in like what is that, right? So what I'm going to do is rewrite it in its other form. And that's a trick. Like if you get stuck on a problem, you're like, I don't really know what to do with it when we're working with logs. One of the things to do is always see, should I write it in its other form? Should I go from log form to exponential or exponential to log? A lot of times, bless you, that is a way of doing it. So this is a common log, okay? It's a base 10, right? Because we don't see a base. So base 10 to the power of what we have on the other side. Let's go ahead and subtract those. That would be 2, right? 7.9 minus 5.9 equals the difference in intensity. So what I was getting at is in math, we probably would have just called that x. Right? We're solving for x. X represents the difference in intensity. Here, the answer is 100. The difference in intensity is 100 times. What this is telling us is the India earthquake, and I'm writing without proper grammar, the India earthquake was 100 times more intense. than it was 100 times more intense than the Greek one. And so think about that. Just 2 points, 2.0 points on the Richter scale equals 100 times more intense. The experience that you have is 100 times more. So next time you hear about those move up exponentially, right? Every point on the Richter scale is pretty exponential. All right, that's it for the homework, the notes. Let us go to the homework. Write it down. So just the odds up to 27. If you want to do more, if you need practice. Of course, I'll put the whole key on Canvas. Do more.